Now, what you saw a bit earlier was a picture of Bill at a machine. He's been here before. So he came here in January, and this is an important part of the program, to have a 4-day induction. And basically, he did physics from 9 in the morning to 9 at night and explored the whole laboratory here, and couldn't resist also recording some of the things at the laboratory here. And you may have a little snapshot and an idea of what may be happening here in the future. But before, and I think it's important to say that 4-day residency is also a way of seeding the imagination and encouraging the artists and the scientists, because during that time I also do a bit of matchmaking. I observe the artists encountering the scientists, and then through that we decide who to put together as the CERN inspiration partner, who will be the person who will guide them through the journey in the labyrinths of CERN. And this year it's been chosen to be Subodh Patil, who is a cosmologist here at CERN.
Thank you, Ariane. And I want to thank both of the speakers before me as well, because they too brought out the fact that perhaps science, the artistic impulse and the scientific impulse are not so separate. Perhaps they're two parts of the same coin. So that leaves me dealing with cliches in my next slide, which I like. Because I think, lest we forget, as Ariane herself remarked before, we are all scientists. When we're children, this is the essential mechanism through which we learn. We do experiments. Sometimes they work out for us, sometimes they don't. But it is through that process, making hypotheses, trying them out, getting them peer-reviewed by your parents, you eventually learn about the world. Art is a big word, but I think we all interface with it because it is an essential part of who we are. It is an essential part of our humanity, and it really does help us make sense of the world inside of us. As a physicist, I'm dealing with a world that's outside of us. There's an objective reality out there, and most of that process involves me having to forget who I am, what my cultural background is, what my biases are, because that will get in the way of me doing good science. But art, if you like, engages that part of us. And, art can be many things to many different people, and sometimes it reinforces this understanding, this intuitive understanding you form of the world and who you are in it and your relationships and the structures you find. But every now and then, you come across art that questions that forces you to reevaluate how you fit into this world, what your relationships are with the structures that you formed in your mind. And what inspired me about Bill's work is that this is exactly how his art affected me when I first came across it. It really does inspire you to reevaluate what you would consider sound and space and your relationship with it, and whether what you're hearing is actually what you're hearing, and how what you hear really affects your relationship with the space that you're in. And what really drove me to put my name forward to be a part of this program is, like many physicists, I have a musical side. I've been a musician as long as I've been a physicist. Many people in my family play some sort of an instrument. It's not too uncommon. And that's it. It's something that I pursue as a very serious hobby. I love to think about it. I love to think about sound. I feel music in a very visceral way. And throughout life, I've engaged in various different projects. It's just a random medley of gig posters and records I've been a part of. And over the next month, I'd hope that the dialogue that is going to happen between Bill and I will not just be about art and science colliding as an abstract thing out there, but perhaps within us, the internal scientist and the internal artist within us colliding. So to talk about my work and how it might relate to sound is that I'm a theoretical physicist. In particular, I'm a cosmologist, and I study early universe physics. And I seek to learn, myself and many other people around the world, seek to learn about fundamental theories by studying cosmology, by studying astrophysical data, by cosmological data. And in some sense, we're trying to reach the same ends as people here at CERN, but instead of colliding particles together, we have another experiment to look at of a much higher energy, the highest energy experiment there ever was, the Big Bang. Or something that looks a lot like it from where we are, because it could just be something that is a nice picture for us to make sense of everything that we see, but there could be something behind it. These are questions that we're out to answer. And the way a cosmologist does this is by, in quotes, listening in. So this is a woodcut, misascribed to come from a 16th century German manuscript. That's actually a piece of Art Nouveau, but it's to represent our intrepid cosmologist from the Middle Ages peering through the first celestial sphere, trying to listen in on the music of the spheres. Because once upon a time in Europe, people thought that the Earth was the center of the universe, and all the different planets and stars exist in spheres around the Earth, and by tuning into their ratios, one can infer some of the harmonies that must exist in our cosmology. So a modern-day cosmologist does exactly the same thing, but with something a lot cooler. The cosmic microwave background can be thought of as the echo of the Big Bang. So sound in this context, you have to reevaluate what that means, because sound does not travel in empty space, but when space is full of stuff, sound does travel. And when the universe was very, very young, it was very, very hot, and all sorts of particles were sort of whizzing around and banging into each other. And what this cosmic microwave background here is, this is a picture of it that was recently given to us by a very incredible collaboration called the Planck collaboration. There was a satellite out there trailing the Earth-Moon system, observing this sound, and it is literally an ultrasound of the universe when it was a baby. And what it is a snapshot of the universe when cooled enough so that light broke free from matter. So the universe was once a very, very hot, dense place. This is what it looks like as if you rewind the film long enough. It was so hot that, and this is the only equation I'm going to throw at you guys today, the most famous equation in physics is Einstein's equation, E equals mc squared. When things have enough energy, because energy can equal mass, when the universe was so hot, when light had so much energy, it could turn into mass. It could turn into material particles. Light could turn into, produce electrons and their antimatter equivalent positrons. And those electrons and positrons can annihilate again and produce light. And this sort of cacophony of events is happening everywhere. And what happens is light can't go very far because it's so energetic it keeps creating stuff. But at some point, the universe cooled enough that E was no longer enough to equals mc squared of the electron, and suddenly light and electrons stopped bouncing off each other, and matter just let go of light. And that moment happened when the universe was 378,000 years old, out of the 13.8 billion years that we think its age is today. So what you're seeing here is that initial flash. That flash is this picture. And it is today everywhere around us in the form of microwave radiation. And in fact, 400 little particles of these lights populate every square centimeter of space everywhere. So in your fingers right now, there's 400 of these guys coming straight at you from this particular moment. And it counts, in fact, for approximately 1% of the static you see on your television. So this picture is color-coded. It's very exaggerated. But what you're seeing is, in fact, a universe that looks the same in every direction you look in the sky, but for the tiniest fluctuations of 1 part in 100,000. So where you see a blue, it's slightly hotter than when you see a red. And by that I mean the photons have more energy or less energy. So what we're actually seeing in the cosmic microwave background is, at that very moment that the universe flashed, you got a picture of the universe where the stuff in the universe that was this undifferentiated slop, we call it a plasma, what we're seeing are the seeds around which eventually all of the stuff that populates our universe is made up of. And so if we zoomed in on one of these little box is a tiny fraction of it, and fast forward that initially almost homogeneous part, and since gravity is an attractive force, things keep clumping towards each other, the universe starts to evolve into something that looks like this. And we inhabit one of these dots. One of these dots in here is one of our galaxies. So when we look out into the night sky, if we look out far enough, this is what we see. And it's explaining that. That is the job of a cosmologist. Where did that come from? How did it get there? So this is a very nice story, right? The Big Bang, fantastic. It's a story. So, but all you've done is, told me some stuff and not given any proof of it, right? So how do we know that this actually really happened? How did we know that this story is really coherent? What's the difference between someone telling you that the universe banged and then all this stuff happened versus someone reading from the book of Genesis or someone reading from another holy text? What is the difference? Well, the difference is it makes predictions. And these are predictions we can go out and verify. And the idea is that the Big Bang itself wasn't the beginning of the universe. There was something even further back that we're still starting to understand. But whatever that was, there was this magical thing that we called inflation, which is when the universe suddenly started to expand really, really fast. And it expanded so fast that it stretched out space to be almost uniform and homogeneous in every direction. And it ended eventually. And inflation is caused by another type of a particle. We're still trying to figure out what it is. It's something. And this field, had energy in it that once inflation ended, it dumped into all the particles it could, and that was the bang that we're seeing. However, you know that if you've ever been in a swimming pool or in a lake or in the ocean, you never see the water being exactly the same height everywhere. There's always little ripples, there's always little fluctuations happening everywhere. And a field in physics is precisely the same thing. A field is something whose localized excitations we call particles. And it is exactly these small fluctuations in the inflaton field that caused little parts of space to be slightly more hotter than others when the Big Bang onset. And that's what we see in the cosmic microwave background. And so by studying these inhomogeneities, we are potentially probing physics at a scale that is 1 trillion times higher than what we can access in the Large Hadron Collider. So how does any of this actually happen? So in order to understand this, I'm going to have to make a little detour into the theory of harmonic analysis, and in particular through acoustics. So a famous mathematician once asked the question, can one hear the shape of a drum? So imagine I blindfolded you and I put you into a room and there was an ensemble of different drums, snares, toms, different kinds, and you had to guess the shape if somebody just hit them. The answer is you can, in fact, do that because of some very remarkable mathematics. So it turns out that intuitively you know this, certainly your brain knows this, your audio cortex knows this, because every sound you hear can be decomposed into a series of pure tones. So a pure tone sounds something like that. Now imagine I add to this tone another tone, maybe a third up. Starts to acquire something like a dial tone. Now imagine I add 2 more. Okay, those are the 4 loudest notes of something that you will recognize immediately when I play the next one, and the difference between the last sound you heard and the sound you're about to hear is 15 more pure tones, but modulated in their amplitude over time. It's the sound of a bell. So I reproduce the sound of a bell just by playing 21 harmonics and modulating the sound. So this phenomenon, musicians know as additive synthesis. This is how all these techs in the Korg or the Roland Corporation make little synthesizers to reproduce instruments. Scientists know this as Fourier decomposition. Okay, that every signal that you hear or see or in anything can be decomposed in terms of its pure modes. Modes being harmonics. Your ears, of course, just know this as hearing. Okay, this is how your brain processes sound. And by analyzing these harmonics, you can, in fact, learn about the material properties of whatever it is that's making this sound. You can hear the shape of the bell. You can, in fact, even hear what it is made up of. You could also tell where it is in the room. Your brain can process phase information If the sound enters one ear slightly before another, you can tell where it is. Your brain is very, very clever. And in reality, sound is made up of a continuum of these harmonics and phases. So imagine I took a violin and I played middle A. So I think it's like, and if I just played the violin at that frequency, you hear something and you process it as middle A on a violin, but in actual fact, there are a lot of different notes that go into making that. In fact, you see a whole bunch of harmonics. So these are all A's, sequentially an octave higher than the original middle A that you have. But then there are all these other little things that don't actually sound like A, and in fact, they're quite dissonant with A. But the sum total of all of these harmonics together make you think that you're hearing a violin. And in fact, the timbre of a violin is generated by, in fact, all of these things that you would have ordinarily considered noise. And the stuff down here at the very lowest frequencies tends to give you a more emotional response. This is just how your brain works. And up here, these frequencies tend to give you a notion of fidelity. So it's the totality of all of these frequencies that make up the sound of a violin. So now I told you about the cosmic microwave background, and I told you that all it is a snapshot of a moment when light finally broke free from matter, and in it we're seeing all sorts of different oscillations. So what is the obvious thing to do? A physicist would take that and decompose it in terms of its harmonics. So if you take all the different notes that could have been sounding in the cosmic microwave background and analyze them, you generate this plot. This is the money plot from the Planck collaboration 2013. It is a remarkable piece of information because by analyzing how loud certain harmonics are in the cosmic microwave background, we can tell a lot about what the universe is actually made up of. So by disentangling the relative heights of these harmonics and where they are, we can tell what the universe is made up of. We can tell something about the speed of sound, or this primordial plasma that tells us what the universe is made up of, and we can also deduce something about the initial conditions of the Big Bang. So what I did was I took this set of harmonics and I sonified them. And sounds like that. And I think that's just incredibly beautiful. And it is through disentangling that we are learning about the early universe. How? Well, like I said, when you know something about the speed of sound in a material and what its different harmonics are, you can tell something about the material that you're in. So what we've learned about is that the primordial plasma that existed in the universe at the time that light broke free conforms to the so-called standard model of cosmology. So in particle physics, we have a standard model, of which the Higgs was the last missing piece. And the standard model, if you like, is just a very fancy name for a Lego set. There are all different little bits of Lego that have very specific rules how you stack them on top of each other. And the tiniest bits of Lego are fundamental particles. And everything else is made up of little stacks of those different things. So quarks stack up into protons, stack up into, atoms, stack up into molecules, stack up into you and me. So that's the standard model of particle physics. Cosmology has one too. And it is a model where the universe is made up of 73% of this stuff. We just call it dark energy. We have no idea what it is yet. 23% of this stuff we call dark matter. Also, we have no idea what it is. And only 4% of this stuff is visible matter. So the stuff that you see in this room, and when you look out into the night sky, you see. So that's pretty weird to realize that 96% of the universe, we have no idea what it is. It looks like nothing that's down here. Pretty crazy. And also that the primordial ripples that were there, around which all the galaxies eventually condensed, did not show a preference for any particular scale. I feel like all the notes tend to be as loud as each other. And on top of this, that these were generated at energies 1 trillion times higher than what we can access at the Large Hadron Collider, up to 1 trillion times higher. So to put a context, physicists love units, and a giga-electron volt is just some unit of energy. The Higgs boson that was discovered here and announced last year on this day has a mass of about 125 giga-electron volts. But the Large Hadron Collider can go up to 1,000 giga-electron volts. These ripples that we're seeing could have been produced at energies as trillion times higher than that. And this is widely accepted as confirming the predictions of this simple picture that we have, that the universe sort of began with this phase of accelerated expansion called inflation, and then the inflation field dumped all of its energy and then caused the Big Bang. But we have absolutely no hint so far as to what the hell the inflation field actually is, what the particle is that's causing it. Some people think that it might be the Higgs. Is it? Could it be something else? We don't know. We're looking for hints. We'd like to know what these hints are, even if they were there, what they might even look like. So maybe they're already lurking in the data. So now I'm going to talk about stuff that I myself work on and why the hell I work at CERN as a cosmologist. Because my research involves borrowing techniques that people use all the time in particle accelerators. And in particle accelerators, people keep looking for physics beyond the standard model because they want to find clues of what might be behind, what might explain what it is we're seeing. There's a lot of things that remain unexplained. I adapt the same tools in the context of cosmology to look for the beyond the standard model of cosmology. And physicists have a name for this tool. It's called effective field theory. It's a very technical thing, but intuitively we all know what it is. And it is the fact that if I were to ask a question, if anybody asks any question about anything, it's quite clear that the answer will depend on what is asking the question and what the question is. So to flesh that out, imagine I ask the question, is a wall solid? Well, if I ask the question with my fist, the answer is pretty clear, the wall is solid. If I hit a wall with my fist, kapow, it doesn't go through, okay? But if I zoom in enough on the wall, I start to see that the wall perhaps isn't this continuum thing that, if I zoom in, that I'll start to see like little paint flecks. If I keep zooming in, I'll see like what the concrete is made up of. Eventually, I'll get down to the atomic level. Then you start to see lots of space in between, these little, the atomic structure. And if I keep on zooming in, it's mostly empty space. So if I ask the question, is the wall solid with a neutrino, the answer is no. It goes right through. So the question you ask depends on what you ask with. But provided you're asking the question at a long enough length scale, the length scale of my fist, it doesn't actually care what the wall is made up of. It could be made up of crazy, exotic things or things we don't even understand, but at the level of the wall, it is solid. So that systemization of parameterizing your ignorance is known as effective field theory, and it works. It allows us to compute and quantify things when we don't know what the fundamental theory of physics is. It's how we even got here. So it's how we can even celebrate finding the Higgs boson. And my work has been generalizing this to time-dependent backgrounds. And a background is the arena in which things happen. So in cosmology, things change in time over the scales that we're interested in. At the Large Hadron Collider, yes, the universe is expanding, but over scales that are completely irrelevant for the experiments that we're doing. And what works at the Large Hadron Collider also works in cosmology, but with some interesting twists and some interesting analogs. And it turns out, actually, that, and this is stuff that I've been working on for maybe 4 years now with many different collaborators, that the process of not caring about very, very small-scale physics has a few subtleties in the context of a time-dependent background, but enough so that you can actually see some interesting things. You can actually see the effect of particles that are much heavier than you think you could access with the experiment that you're accessing. And so what we find is that the inflaton field likes to talk to everything that it can possibly talk to. That if it is eventually going to dump its energy into all the stuff that makes us up, it must talk to them in some way. And in the process of that talking, you can excite some very, very high energy fields, consistent with us not having to know the full theory. In physics terms, it's known as decoupling. And what you find is that there are transient drops in the speed of sound of the ambient plasma during inflation that can manifest in bumps in the spectral analysis of the cosmic microwave background. So if we took its noise and decomposed in terms of its harmonics, it results in little bumps, just like what happens in a particle physics experiment. So this here is a famous plot from the CMS collaboration. Sorry, Atlas guys. And what we see here is a little bump in the energetics of a particular process that betrays the existence of a particle that we know of as the Higgs. Same thing could happen during inflation, where different particles that you haven't seen yet betray themselves through bumps in the echo of the Big Bang. So it could potentially tell us what the inflationary field is, what it is, how it embeds itself into any fundamental theory. If it's the Higgs, it'll let us know. It might even allow us to falsify the paradigm itself. We'd be fools to think that we understand everything at all times. But as a scientist, it's very hard to imagine anything else. But you must always allow for your theory to be incorrect. That's what makes us scientists, and not high priests. So, and of course, all of this work is done with a bunch of people from all over the world, and that's it. So just like the philosopher of the woodcut, sticking our head through the celestial sphere, trying to listen into the music of the spheres, we're trying to do the same thing, except we're blindfolded and partly deaf, and we've never even come across some of the instruments whose shape we're trying to hear. But they're out there, and we do it. And as a collective of hundreds of researchers across all the continents, we've come remarkably far to even have this story, have a consistent story that we can at least tease and poke and test. But we still have a very long way to go. So for that, you have to stay tuned. So thank you very much.